Okay, let's look at distributions in another way. Characteristics of a normal distribution, and you saw this in the previous normal distribution slide. The mean, the median, and the mode all fall at the same place in a normal distribution. This is the mean, the median, and the mode. And see, that's that mu Greek symbol for the population, and these are the standard deviations. Plus 1 standard deviation, plus 2 standard deviations, and plus 3 standard deviations. And you see the same thing on the other side, just negative. Minus 1 standard deviation, minus 2 standard deviations, minus 3 standard deviations. The data in a normal curve, this is the normal curve. Sometimes it's been called the bell curve. The data are continuous. They are symmetrically distributed around that central point. And you see that characteristic of the normal curve that's so critical to statistics, and that is that 68% of the data points will fall within 1 standard deviation from the mean. 95, if you add these numbers up, 13 plus 34 plus 34 plus 13.6, 95% fall within 2 standard deviations. That's 95%. And then 99% fall within the 3 standard deviations. So if you add on this 2% and this 2%, you get the 99%. This was 68. And you can see that just by adding those percentage points. That's an important characteristic to remember for a normal distribution. But there's different kinds of distributions. Remember, we're still just talking about one variable. One variable, the distribution of one variable, values of one variable. It can look different. Rarely do we have a perfect normal distribution in our data. And so sometimes they're off. And what I mean by that is things like this. Your distribution could look like these graphs show. These graphs show skewed distributions. Skew, that's how you spell skew, and it stands for a lack of symmetry of the data. And it's a little counterintuitive when you see a distribution that looks like this to call it negative, a negative distribution. I always have a tendency to say, okay, if it's skewed like this, it looks like more values are over here on the right-hand side, but it's actually named in a counterintuitive way, if you ask me. If a distribution that looks like this is negatively skewed. There are more values that would happen in this than you would ordinarily think or compare to the normal distribution. So this is negatively skewed as the tail is elongated to the left towards the negative side. And just the opposite with this distribution, the distribution on the right-hand side. It's positively skewed as the tail of the distribution is elongated to the right. There are more data points in the tail here than you would ordinarily expect. And that creates the skew. It's a measure of symmetry, and the central measures of tendency can be affected by skewness in the distribution, meaning that there are more cases to one side than the other. The skewness for a normal distribution is 0. If you don't have a normal distribution, you can actually test for skew, and I'll show you how to do that when we start computing and running analyses in SPSS. But the values that could be acceptable limits for skew would range to from plus or minus 1 to plus or minus 2. So even as you go all the way up to plus 2 or minus 2, you can still use parametric statistics with that level of skewness. Another distribution characteristic is kurtosis. So we have skew and kurtosis. And kurtosis is the measure of, let me get my pen, is the measure of peakedness of a distribution. So you can see here with the different curves, this is more peakedness, and so the kurtosis statistic will be higher. And this blue one is less peakedness, and so the kurtosis value will be lower with that one. So it's a measure of basically how flat the distribution is, or conversely, how peaked the distribution is. Don't feel like you have to remember these words. They're on here to show that that really high peak curve has a positive kurtosis, and the blue curve, the flatter curve, has a negative kurtosis. Like skew, when you test for kurtosis for your variables, acceptability is probably in the plus to minus 2 range. That's usually considered acceptable, and you can continue to use parametric statistics for that. The nice thing about normal distribution is that it has mathematical characteristics or properties, and parametric statistics are based on those properties. And so as much as the distribution can get close to the normal distribution, which you can see on this chart is the green curve. I'm going to finish this word, parametric. Then as much as the distribution can represent the green normal curve, parametric statistics are based on the characteristics of that normal curve, and you can use the parametric statistics. Mostly the ones we're going to be learning about in this class are parametric statistics. When you have skewed data or high kurtosis one way or kurtosis in the other direction, then you actually have to use non-parametric statistics. They're less robust, and so they may underestimate the size of the relationship, or they may underestimate the size of the associations in the data. Okay, so these are the words for the descriptive statistics that we use to represent one variable. But let's look at what it might look like. How do you visually represent one variable? Well, it depends on your level of measurement, of course. When you have categorical variables, you can use bar charts to represent the data visually. And so here's an example of a bar chart looking at number of students. We have this many students that took this little quiz. What's your favorite juice? Red, orange, yellow, purple. And you use the bar chart to show how many students said each response category. So 6 people said they liked purple juice, 10 people said they liked yellow juice, 8 people said they liked orange juice, and 2 people said they liked red juice. That's just one variable with 4 response categories represented on a bar chart. The nice thing about representing data visually is that right away you can see what the most frequently response category was answered. And so in this case, right away you can tell that the mode was yellow juice. And, I mean, this was nominally measured variable. These were just labels for juice, different kinds of juice. And that's the proper level, that's the proper measure of central tendency for nominally measured data for variables. For interval and ratio level data, a good way to represent the data visually is with what we call a histogram. And with this, we're just looking at scores on the ACT math test. And the mean is given here because the mean is the appropriate measure of central tendency with interval and ratio level data. The mean on the ACT math test is 20.9. We have a standard deviation right here of 4.1, so that tells you the dispersion of the data. And then we have an overall N. So this data represents information from 522 students. You actually can pick out, you might actually be able to pick out the mode here if you took this very tall bar down. And it's about right here, so about 21 was the mode. And there is a curve superimposed on the histogram. And I don't know about you, but this histogram looks like it's experiencing some peakedness. So I would contend that it has a positive kurtosis statistic. But you could find out whether or not that was going to cause problems for you in your data analysis going forward by running the kurtosis statistic. But just by looking at it, just by looking at the distribution, you can tell. You can tell those things about your data. That's why it's nice to give visuals. Okay. And that's all we're going to talk about in terms of descriptive statistics for one variable. Next, we'll talk about descriptive statistics for representing the relationship between two variables.